All right, let's talk about gases and tons of equations and probably more than you need or want to know about gases. But I honestly went down a rabbit hole. For me, understanding the nitty gritty of how the O2 and the CO2 levels change helps a lot with future pathologies. But again, don't feel pressure to understand, no pun intended, to understand everything. We'll go into the alveolar gas equation, bunch of stuff about gas pressures and little tidbits, conundrums, fun facts. Henry's law, decompression sickness. Alveolar gas equation. All right, so big A always means alveolar. Anytime you see little a, it always means the artery. So how do we figure out the concentration of oxygen in the alveoli? Well, you can't just stick a needle in the alveoli to measure the pressure. That'll cause a tension pneumothorax, right? Or at the very least, a traumatic pneumothorax. You can't put an esophageal tipped balloon into the thorax because that just gets the intrapleural pressure. We want the intrapulmonary, intraalveolar pressure. So to do it, you have to use this fun equation. So this is the fraction of inspired oxygen. It is always 21% unless somebody's in a hospital and they are having supplemental oxygen, in which case it might be like 100%, and they could change the value. Atmospheric pressure, water vapor pressure, both of these things together are really going to be the amount of oxygen that hits your alveoli, minus this, which is the amount of oxygen that leaves the alveoli, that is consumed. And if you do the amount that enters the alveoli minus the amount that leaves the alveoli, you have the alveolar oxygen content. Specifically, how we get the amount that leaves the alveoli is the arterial CO2 pressure divided by the respiratory quotient. We'll go into this all. So as we said, this is really just like the sort of the concentration of oxygen in the alveoli, big A for alveoli. You could probably just memorize that it's around 100, CO2 is around 40. Now, atmospheric, we have 760 units of atmospheric pressure times 0.21 is like 160. So if it's 160, why is it 100 there? The reason is that water vapor and carbon dioxide lower the value. And we'll get into that. So 760, like we just said, this is about 21%, and this gives us about 161 in the atmosphere. Notice that there's almost no CO2, and there's a bunch of nitrogen, which we'll get to. Weirdly, argon, but let's ignore that. So why does the water vapor bring it down? Well, when you when you breathe in, when you inhale, you're breathing in 760 torr atmospheric air. And this is dry. There's not that much water in there. But when you breathe out, you're breathing out a lot of water vapor. And when the air is coming in, you have even more water vapor in your pharynx, in your trachea, in your mouth. And the water vapor sort of competes. It pushes out a bunch of the gas that would otherwise get in, right? We're not entering into a complete vacuum. So if it's 760 out here at functional residual capacity, also is going to be 760 there. But again, there's a lot of water vapor on the inside and there's not as much on the outside. So the 760 that you inhale that comes in to your respiratory tract is going to be 760 dry plus wet, which means there's less, that 160 value of oxygen has to come down. So specifically to get, really the dry atmospheric pressure, the dry oxygen value, it's 0.21, but not times 760 minus the water vapor pressure. You do something similar to this when you collect stuff over water in Gen Chem. And you also see these little vapor pressure trees, and 37 degrees Celsius, it's about 45 atmospheres. So 760 minus 45 times 0.21 is about 150. So that is the amount of oxygen that's getting into your maybe like your trachea, your bronchioles. However, we also need to keep in mind that the oxygen that gets into the alveoli, well, it's just as quickly, a lot of it's going to get sucked into the pulmonary capillaries. So if 150 comes in, I shouldn't expect it to stay 150. And how the heck do we figure out how much oxygen is being consumed? That seems complicated. And it is complicated. There's a very clever but complicated mechanism to figure it out. It's this equation here. So a couple things. CO2 fully equilibrates in the alveoli with the pulmonary capillaries, which means when I detect the pulmonary arterial CO2 pressure, it is about the same as the alveolar pressure. And that's going to often be true. So the alveolar pressure is about the same as the arterial pressure. So And again, we can't just detect P big A CO2. You can't poke a needle in the lungs, but you can do an arterial blood gas draw to detect that value and say, oh, okay, interesting. The PA CO2 is something like, I don't know, 40. But again, I want the oxygen consumed. I don't care about how much CO2 is in the alveoli. Well, remember that like cellular aspiration, the amount of CO2 you generate is pretty proportional or correlated with the amount of oxygen consumed. And you might go, oh, wow, okay, genius. So if there's 40 units of CO2 in the lungs, that means that we must have used 40 units of O2. Almost, except that not everything is carbo. We don't just, it depends. If you're only eating raw glucose, then maybe it is 40 equals 40. But we're also eating a lot of fats, and in a Western diet, we have a different metabolic pathway for this. Notice here, 145 with 102. So this 1-to-1 ratio gives us what's called a respiratory quotient of 1. This 145 to 102 gives us a respiratory quotient of 0.7. At the end of the day, it varies from person to person. It's going to be about 0.8 in a Western society. So 40 units of CO2 in your alveoli really means that we must have consumed 50 units of oxygen, which means 50 units of oxygen leave the alveoli. So if we have 150 units of O2 coming in and 50 units coming out, that's where the 100 units of O2 kind of more or less sitting in your alveoli comes from. Now, that's good to know, but honestly, a much more useful heuristic that you'll see a lot is that CO2 in the alveoli will crowd the alveoli. More CO2, kind of like similar with water vapor. If there's more CO2 here, it's difficult for more O2 to get in because it's already occupied by a lot of CO2. So we're going to consider them mortal enemies. If CO2 is high, O2 is going to be low. It's a very useful rule of thumb. And you could also just think about the formula, right? If this is my formula, the alveolar oxygen value is if I increased this just in the formula, just mathematically, for ignoring the concepts, if I increase that value because it's a subtraction, this value will have to go down. So we can think of this. You can think of them being mortal enemies, or you could just literally go ahead and look at the formula. 3 different ways to come to that conclusion. All right. So the formula, in a nutshell. The alveolar oxygen is the amount entering minus the amount leaving. The amount entering is the fraction of inspired oxygen, 21. We have to subtract the water vapor to get the dry air, and then the amount leaving. The amount leaving is, the arterial CO2 pressure is really the same as the alveolar CO2 because of perfect diffusion and equilibration, but we get about like a 0.8 ratio, right? So every 10 oxygen consumed will generate about 8 CO2. So we have to divide by 0.8. And so we get this 150 minus 50. And so we have about 100. So again, 160 comes in. It's 150 when we consider that's humidified. And then it's 100 here. The CO2 values, on the other hand, are going to be, there's very little in atmosphere. It's going to be about 40 in here. And it's probably good just to focus on this. Oxygen, after it goes through the tissues and is used up, is about 40. The CO2 value is about 46. And when they leave, it's going to be 100. We picked up a bunch of oxygen. We dumped off a little bit of the CO2 going from 46 to 40. It's actually the arterial oxygen is usually going to go a little bit lower, actually. It's going to go to 95, which is weird, which we will talk about right now. All right, so again, I'm going to go a little nitty gritty with a lot of this stuff. So, feel free to, I guess, tune out a little bit. A lot of it will be relevant and helpful, but just don't, it's not super high yield. I just wanted to understand it. And I felt I was running into conspiracy theory after conspiracy theory with how they were explaining it online, made me go a little crazy. So weird tidbit, conundrum, conspiracy theory number 1 to tie up. Shouldn't we just expel all of the CO2, right? Why do we have 40 CO2? Shouldn't it be maybe like 40 CO2, but then 0 CO2, like after we exhale? That seems weird. So that's number 1. Number 2 is if we looked at this, if this is 40 and 46, well, why does it perfectly match? And this is 140. Why is this now 140? How do the pulmonary capillaries or really the pulmonary veins now become identical to the alveolar pressure? And why didn't the alveolar pressure change at all, right? Shouldn't this value change that value? That just seems super weird to me. 3, why is the pulmonary arterial oxygen lower? Yeah, so I just said that this, in the pulmonary capillaries, it'll be 100. But quickly, as you go into the pulmonary artery and just the systemic arteries, it dips to 95. That seems weird. Why does it dip? 4, Why is it that it's 45 for CO2 and it's 100 for O2? Again, shouldn't it be kind of close to being the same? Or a different way to think about it is the idea that the amount of CO2 entering the alveoli is about 5. So it was 46 in the pulmonary artery, and then it was about 40 when we look at the pulmonary vein. So why this drop of 6, this drop of 5, while the gain in oxygen is about 60? We have 40 in the pulmonary artery, and we have 100 or 95 when we consider the drop a little bit after the pulmonary vein. So that's another way of articulating mostly the same question, the same point. And then lastly, if nitrogen is so abundant, right, it's like 78% of air, why don't we see it as part of this whole system? So let's go through these one by one. Hopefully it'll shed a little bit of light on how all of this is working. Well, the reason we don't expel all of the CO2 is that you got to remember, this is a tidal volume breath, right? You can fit, I don't know, 5 or 6 liters of oxygen gas in your lungs. You're only normal 500 in, 500 out, unless you're taking a super deep breath in or super deep breath out. So that's 15%. This 15% is going to mean that we're not going to drop all of our CO2. We're going to drop a small value. 2, why does the capillary gas value equal the alveolar gas value? Well, there's equilibration. CO2 diffuses super well. Oxygen diffuses pretty well. And in a normal, healthy person, if I have 45 units of CO2 as it's coming into the alveoli, quickly the CO2 is going to become in equilibrium with the alveoli, and the alveoli one is at 40, so it's going to bow and become 40. Same thing over here. It's 40 coming into the alveoli, the pulmonary artery, and as it's leaving the capillaries, the pulmonary vein now is going to be about 100. It's going to match what the alveoli is. So it's perfusion limited. It's going to fully diffuse, and equilibrium will be reached. That doesn't really answer the question, right? Because we should still say, okay, wait, it's an equilibrium. Well, then why doesn't the alveolar gas meet it halfway, right? Shouldn't that value change? The reason it doesn't is because the amount of gas in a capillary is usually about 100. Or at least like the amount, if you take a snapshot in time, the volume of capillary that's wrapped around an alveoli is about 100, while the alveoli itself has about 3,500, 3.5 liters of gas. So it's like a drop in the ocean, right? It would be like dropping 100 milliliters of 20-degree waters and 3.5 liters of 100-degree water, and then being surprised when the final solution is like 99.7-degree water, which we can more or less just call 100. So the truth is the alveolar gas values do change a little bit, but it's a negligible value, right? We're saying that it's more or less staying the same because its volume of gas there's just so much more here than there is here. So it makes sense that these values shouldn't really change, and then these values will, at the end of the day, become identical to the alveolar values. All right, well, why does the arterial value drop? We've talked about this before. There is a dual blood supply to the lungs. There is also a bronchial artery that's feeding the lungs, and that if there's a bronchial artery, there must be a bronchial vein, which is deoxygenated. We know that deoxygenated is 40. So if this is 104 in the pulmonary capillary, and now here we're coming into the pulmonary vein, the pulmonary vein is going to combine with the pulmonary vein is oxygen rich. The bronchial vein is oxygen poor because this is like a normal vein, and this is like our one weird pulmonary vein that's oxygenated. And they're going to mix here, and this 104 is going to drop to 100. And don't take these numbers too crazy seriously, right? If I say 104 to 100 or 195, tomato. Alternatively, a VQ mismatch, we don't have perfect ventilation perfusion ratios all of the time. Sometimes I might have some alveoli that are just stinkers. They're pulmonary edema, there's pneumonia. Who knows what's going on? Maybe there's fibrosis, the fusion stinks. Maybe I have a shunt. Maybe I have a little bit of a PFO. There could be tons of reasons that some of these pulmonary arteries just don't ever pick up any oxygen. So they were 40 and they stay 40. They stay 40, stay 40, stay 40. Now these numbers are misleading. In this picture, we can assume that there's a few bad eggs, a few bad pulmonary arteries, and mostly good pulmonary arteries, now pulmonary veins, that are having perfect diffusion of gas. So there's a bunch of these hundreds, a few of these 40s, but when they mix, it's now 90. So this would be a VQ mismatch issue. Ideally, this is somewhat mitigated by hypoxic vasoconstriction, where I'm going to reduce the amount of blood flow that's going to these bad alveoli so that this number, instead of 99, might be like 98, and it's not as big of a deal. But I would say that this is probably the main reason to account for the drop from here to here. All right, so why in general is the alveolar CO2 pressure, we said it was like 40 versus the 100 of PaO2. So things about to get really complicated. Again, don't have to know everything, but I do find it helpful, at least personally. So the amount of, let's just think about this. This is just a straight up, we just did this, the alveolar gas equation, right? How much oxygen gets into the alveoli from the atmosphere? It's 150 once we take the humidification into account. The amount that leaves is the amount of CO2. Should be about 50 that's leaving. So we have about 100 oxygen that sits in the alveoli. What about the CO2? Well, we're producing about 45 units of CO2 in our blood. And when it gets into the pulmonary, when it gets into the alveoli, well, the endothelial and epithelial tissue, the pneumocytes, they're cells, they're living, they're generating a little bit of CO2 as well. So it should go 45, 46, 47, goes up a little bit. Now this 0.85 is that we take into account that we are breathing out and we're breathing in air that has almost no CO2. So it's kind of like 0.85 times like 47 plus 0.15 times 0 because there's no CO2, right? It's the amount we're looking in the alveoli is an average. And so this 0.85 times like 47 times plus 0.15 times 0 is going to give us about 40. So that is like the average of the inhalation and the exhalation values. All right, it doesn't fully explain everything, right? Because we could still ask ourselves, okay, well, let's not look at it from the alveolar perspective. Let's look at it from the tissue perspective. Why is it the case, we just take it for granted that it's producing 45? Why doesn't it produce 100? Two things. One, remember the respiratory quotient. If you consume 10 oxygen values, you should produce about 8 CO2. So the value should be a little bit smaller, first of all. But second of all, we have excess oxygen. That's the whole point, is that we have tons of reserves. You shouldn't have reserves of CO2 because that's garbage, that's trash, that's the byproduct that's being generated. So because we have reserves and we're going from like 100 and we're dropping off 37 or 38% or whatever, we're still going to have a little bit left, right? We're going from 100 to 40. We're not going from 100 to 0. We're not using it all. So there should be more oxygen than CO2. But that still doesn't fully, it's still a bone to pick with this. Because if we just look, whether you look at the alveolar change or the tissue exchange, it's kind of the same issue. Let's look at the tissue exchange. Here, my oxygen value was 100 because of the bronchial vein dilution. It's now 95. So, okay, 95. And then, on the venous end of the capillary, it's now 40. So I went from 95 to 40. So it's a 55 exchange for the O2. Well, what about the CO2? The CO2 goes from 40 to 45. So it's a gain in 5, 40, it should be minus 5. It should be 45 minus 40 equals 5. There we go. So it should be 5. So in other words, why doesn't the 55 drop in oxygen equal the gain of 5 in CO2? And, we just talked about the respiratory quotient, but that's not enough to account for this tremendous disparity. So how do we explain this? First is just a reminder that the amount of pressure we see in solution is really just to do with the dissolved amount of gas, not the total amount of gas in the blood, the amount dissolved in the blood. Second is that sequestering proteins like hemoglobin, they might increase the solubility of something, but increasing the solubility doesn't necessarily increase the amount of dissolved particles, so therefore it might not increase the amount of pressure. So let's look at this. We have 6 orange things in solution. So 1, 2, 3, 4, 5, 6, 7, 8. I'm trying to think. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. You know what? I'm going to go off on a limb, and I'm just going to call this 8. Maybe it's 6. Doesn't really matter. So there's 8 things in solution. So let's say that the pressure is 8, and then the solubility is 8. Okay, well, what happens if I put a bunch of sequestering proteins in here that bind to these things? This throws off, so we had an equilibrium. Every one that leaves accounts for one that enters. But now we have a bunch of sequestering proteins. I have less proteins that can leave, which means more will come in than will leave. So this throws off the equilibrium. So again, like we said, there's more coming in than will leave. So over time, we're just going to note that we have a increased solubility. Solubility means the maximum amount of gas particles that could get into solution. I count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. But in terms of the free values, the free dissolved particles are the only one actually contributing to gas pressure. it's still 8. So notice that the adding the sequestering like hemoglobin like protein increases the solubility, but it does not necessarily increase the pressure because the amount of dissolved particles at the end of the day is more or less the same. That's just a general concept, a general rule of thumb. The point being that the minus the 55 loss and the 5 gain, there might be more going on behind the scenes with the solubility and sequestering proteins and secondary formation reactions and things like that. So starting with the oxygen, its solubility is considerably increased by sequestering hemoglobin, like we just saw in the last slide. What we talked about in a previous section, the dissolved O2 is a very small proportion of the overall O2. The hemoglobin holds on to a vast majority of the oxygen. So this is the only thing that's directly accounting for the pressure. So again, there you go. So CO2 is even more complex. Its solubility is altered. It does bind to hemoglobin a little bit. It also, majority of it is stored as bicarbonate through this reaction, which we should be familiar with, which is powered by carbonic anhydrase. And it forms better non-covalent bonds, so it has increased solubility. Oxygen is nonpolar. This is also nonpolar, but at least there's a dipole moment where this negative could be attracted to that positive. So CO2 is about 25 times more soluble in even just water, I think, than oxygen. So I would know that CO2 is about 5% dissolved in the blood. The bound to hemoglobin is going to be about 25%, and then the bicarb is going to be about 70%. So again, CO2 comes in, some of it binds to the carbaminohemoglobin, binds to the N-terminus of one of the polypeptides. Carbonic anhydrase makes it by carbonic acid, which becomes bicarbonate and an H+. The H+ binds to the hemoglobin, stabilizes the tense conformation. This is really just what the Bohr shift is. And then we have the exact opposite process happening in the alveoli. So if we could measure, just to understand at least this second point, if you can measure the pH at the arterial versus the venous end of the pulmonary capillaries, what would you see? You have way more CO2 on the arterial end, which means you should have more H+, which means the pH should be lower. But after you breathe a bunch of the CO2 out, this is going to move down, which means Le Chatelier is going to shift everything to the left. I'm going to lose H+, and if I lose H+, the pH should increase. This is just a better picture. CO2 can become, bicarb, which goes out here. The H+ can bind, this is the Bohr shift, stabilizing the tense, kicking off hemoglobin. Some of it binds to the amino terminus, and about 5% or so is just dissolved. But again, this dissolved one is the only one that actually contributes to PCO2. All of this to say that at the end of the day, I don't really have a good answer. I mean, it's really difficult to get any precise quantitative conclusions without knowing the weights and balances of different considerations. But just, I guess, 2 last things. So not only is CO2 more soluble, so being more soluble just means that we can squeeze in more CO2, or at least more easily with less pressure. But it's actually also dissolved more. Remember that solubility and being dissolved are different. So 5.9% of CO2 is actually dissolved compared to 1.5% of oxygen. This might make somebody think that therefore CO2 is going to be a higher pressure, but this is likely offset by a larger total amount of oxygen gas, despite the higher concentration of the CO2 gas being dissolved. Additionally, the oomph that a partial pressure exerts is going to depend somewhat on the solubility of that thing in solution. So the partial pressure is equal to the concentration of the dissolved gas divided by the solubility coefficient. One way to think of this is that the pressure, if we say that PO2 is 40 in the gas, what we mean is that if we had, this amount of blood in a beaker, the vapor pressure necessary to push that particular amount of CO2 into solution would need to be 40. So the vapor pressure would need to be 40 to get X concentration into the solution. And if something's really soluble, S equals Kp, Henry's law, we don't actually need a large pressure to push a certain amount of it into solution. We can see that here with an example. You can imagine something that's 10 times higher solubility in a lipid than in a water. So it's really easily dissolved in a lipid. So we have a lot of it. The contents is 100. and the pressure is 100. On the other hand, for water where it's not very soluble, maybe we have way less. We only have 10 units of this particular mystery compound X. And yet the pressure is the same. And again, if you think of it over here, it's because for the liquid, we would need not that large of a pressure, just 100, to push a huge amount of this into solution because it wants to go. While if you're looking at the water, you would need that same pressure just to even push a small amount in because it's not very soluble. Point being that because CO2 has such a high solubility, it might not quite exact the same amount of pressure as an equivalent amount of dissolved O2. Enough with this. This is all just food for thought. Lastly, is just to consider the nitrogen. So if nitrogen is the dominant thing of atmospheric composition, why is it not ubiquitous in our blood, right? It's 78% here, so why don't we talk about nitrogen in our blood? Why doesn't it get through? Well, it turns out it does get through. We just don't really talk about it because it's inert. It's not reactive, right? Nitrogen has this triple bond. It doesn't really want to react with things. It's happy as a clam. It is a great stable, low energy condition. So this is atmospheric, then inspired, alveolar, arterial. Notice we still have a lot of N2. N2 makes its way into our body for sure. It just doesn't do anything. So Henry's law, again, solubility is the total amount that you can put into a liquid before it becomes saturated. This depends on the solubility multiplied by the pressure. So a couple of things. Oxygen, 0.013, CO2 is 0.034, carbon monoxide is 0.0095, and this is 0.0061. So all of these are low K, low K, low K. Now, we have a high solubility of oxygen in our blood because it's a particularly large pressure. CO2, I guess we have a large amount in our blood, but that's largely not because of the pressure is necessarily high, but because its solubility is so very high. And then for carbon monoxide, the solubility is increased by hemoglobin. CO2 is increased by hemoglobin. Also, its conversion to bicarbonate. And then carbon monoxide is also technically increased by hemoglobin, but it's luckily not very abundant in the atmosphere. So nitrogen has a low solubility constant, but it's so damn abundant that it pushes its way into solution anyways. Everything below of this is really just articulating something that we've already seen with bicarb. You see this, the solubility product constant equilibrium in GenChem. If I want to dissolve a little bit of silver chloride into solution, it'll have this particular solubility, which is just pure water. If I want to dissolve it into the same solution that has a little bit of ammonia, and if I know that ammonia has a very favorable forward complexation reaction with silver, the idea is that all of the silver that dissolves will be consumed in this second reaction and going forward. So this drops this, which makes this even want to dissolve more and more and more and more. So the solubility increases. So we see the same thing with the bicarb and CO2. The conversion into bicarb is going to drive the not necessarily the dissolving like here, but the solubility, the desire to go from the gas phase into the liquid phase. So what happens with nitrogen? So we have my friend Jeff, now we got my friend Mitch. What happens if you go into Thailand and you go diving? So the pressure is relevant here. The increased pressure when you go underwater, if this is my scuba tank at atmospheric conditions when I'm in land, when I go deep underwater, not even that deep, even 50 meters, it's going to compress all of this gas into a very, very small volume, this high pressure of gas. So this is the alveolar gas equation, but instead I've just made it for nitrogen. The idea is that 760 now becomes a lot when you go underwater. And so we had a little bit of this going to our blood. Now I just have a ton. I just have a ton of nitrogen going inside of my blood when I go underwater. Now you might think, wait a second, why? That's not just nitrogen, and you'd be right. Technically, this would happen for any gas that is under high pressure when you go scuba diving. The reasoning is that really the scuba tanks though only contain nitrogen, helium sometimes, and this could be an issue, except that it's usually pretty high cost to have helium in your scuba tank, so it's usually just going to be nitrogen. Even still, nitrogen is higher. Oxygen is also in your scuba tank, obviously, because that's what you're breathing in to live, but it's sequestered by hemoglobin, right? So if I double the amount of pressure of my inspired oxygen, that doesn't necessarily equate with a double the amount of dissolved oxygen in my blood. So a lot of it gets soaked up by the hemoglobin. So the main one that we're really worried about is the nitrogen, maybe the helium, maybe the oxygen a little bit, but I'd say mostly the nitrogen. So here's us close to the water. When we go underwater, the higher pressure pushes nitrogen through the alveoli into our blood. Now we have more dissolved nitrogen. Now that in and of itself is not dangerous. The problem is if you come up too quickly, now the nitrogen that's dissolved, the solubility decreases and it starts to precipitate and it forms these bubbles. Very much like we see in gin chem. You have an unsaturated solution, a saturated solution, and supersaturated. Supersaturated, the concentration is higher than wants to fit in the solution, and so it'll start to precipitate and form crystals. Here, instead of precipitating and form crystals, it'll form bubbles. The same thing happens when I have a Coke. It's high pressure. This higher pressure makes all of my particles dissolve safely into the solution. But you know what? When you open it and you let all of this gas out, the pressure becomes low. The pressure going low changes the solubility. It now is super saturated and it's going to start to bubble up and precipitate out of solution. You get these large bubbles seen here, and the same thing happens in your blood. You will get nitrogen bubbles. Could be a helium bubble as well.